You're watching Force 13's live streaming service.
Hello everyone and welcome to Astronomy Hour here on Force 13. I am Devin Williams here, and man, I got a little bit of an interesting topic I want to go over today, because what we're going to be talking about is degenerate stars and extreme gravitation. What that means is we're basically going to be going over white dwarfs, neutron stars, black holes, all the fun stuff when it comes to space. So I wanted to start off with the solar system here, as I pretty much normally do for all of these things. And mainly I want to start off with the sun, because of course, you know, it's the sun. So what's going to happen here is that, of course, after 5 billion years, the sun's going to eventually grow up, become a red giant. It's going to become huge, and it's eventually going to shrink down, act down after another billion or so years after becoming a red giant. It's going to become a white dwarf. What are these white dwarfs like? Well, these white dwarfs, at least for stars of the sun's size, which we have seen go through its entire evolutionary process, so we know that it's going to be a carbon-oxygen-based white dwarf. And these white dwarfs are something that we call electron degenerate. Now let me go ahead and pull up one of the simulations I made here with a white dwarf, just to show you what one of these things look like here. So a very famous white dwarf is actually the companion star of the brightest star in the night sky. It's Sirius, and this one is Sirius B. And this is very hard to spot in the night sky. You go ahead and you take a look at it. Through a telescope, you might be able to see it, but it's pretty hard to spot because of how small it is. And how small is it? Well, you can see here it's a radius of about, 6,000 kilometers. So it's about the size of the Earth, but it contains the mass of the sun. So as you can imagine, an object this dense packs quite a lot of gravity. What's the surface gravity of something this dense, something this insane? Well, it's something along the lines of 380,000 times what the surface gravity of Earth is. But then you think about that and you think 380,000 times the gravity of Earth. Now that's incredible. That would suck everything in the solar system right in. Well, the thing is that that's the surface gravity. What really only matters here is that it's pretty much only the mass of the sun. So I go ahead and I play this simulation out. Nothing in the solar system changes. So the only time that gravity really starts getting extreme is when you actually go inside the sun's radius and you start going very, very close in on one of these. And it's going to be the same for neutron stars and black holes. So that's basically how this works. And look at this. This is just beautiful. You have the white dwarf sitting at the center of this solar system. Everything's just going along just like nothing ever happened. All I did was replace the sun with a white dwarf. Everything is fine gravitationally. Even the outer planets are having a good time. Of course, obviously, with the white dwarf being at the center, there's virtually no energy being emitted here. So the Earth is now a giant ball of ice. And you can see the temperature slowly going down and down and down and down and down. That's going to eventually go to the coldest possible temperature in the universe, which is going to be about negative 270 degrees Celsius, which is the temperature of the cosmic microwave background radiation. But what are these things made up of anyways? Well, as I said at the top of the stream, these things are made of something called degenerate matter. And this degenerate matter is a very, very strange type of matter because it's still one of those types of plasma that it's still a type of matter here, but it's not like a solid, a liquid, or gas. It's not anything like that. It's really, really weird in the fact that all of the atoms inside this star are packed so tightly together. All the electrons are packed so tightly together that quantum mechanically, you cannot physically pack the atoms any tighter. So what you have here is a state of matter that we call electron degenerate. And this electron degenerate matter, of course, you would imagine, is very, very dense, like this star. But it's not the densest that we can get, if you would believe that. Now, of course, electrons are very small. So small, in fact, that us physicists, we pretty much just call them a point particle. Essentially, that's what they are. They are a point. It's not like a proton or a neutron, which actually has a volume. The electron doesn't have a specific volume to it. There's really no volume of an electron. So it's basically considered a point. So you think to yourself and you say, well, you ought to be able to pack points very, very tightly together. Well, no, because you have the protons still there. So all the protons of all the atoms on here, they're still there. So obviously, all the protons, the proton interacts with another proton, they're wanting to repel each other. The electron interacts with the other electron, they want to repel each other. And their force of repelling is so strong, but the pressure inside one of these things is so great that it's able to just smush everything together and just make it as compact as possible. Now, within one of these white dwarfs, specifically one of these solar mass white dwarfs like Sirius B, there's going to be two states of matter in here. There's going to be non-relativistic and relativistic degenerate matter. And basically, the difference between the two is how dense is the matter packed inside of it. For white dwarfs of about 3/4 of the mass of the sun, those electrons are all throughout the white dwarf star. Those are going to be moving at non-relativistic speeds. They're not going anywhere near the speed of light. Even though they're all packed together, they can still move around, which is another weird thing with quantum mechanics. So they're all packed together, but they're not moving around at speeds nearing the speed of light. However, when you pack them really tight, they are going to be like that. So what happens is when you actually increase the mass of this, you end up getting this relativistic degenerate matter, and it actually ends up making the white dwarf more compact. You don't add mass and add the radius. That's not how this works. It's actually the exact opposite. The more massive the white dwarf, the smaller it ends up getting. And there ends up being a critical mass, which a white dwarf could end up receiving. And this is well known as the Chandrasekhar limit. And it is approximated to be about 1.44 times the mass of the sun. Now, we know this very well because we have actually just studied electron degenerate matter with our nuclear bomb testing programs. We actually know a lot about electron degenerate matter. We actually have equations that describe it. So we know pretty well. But we also know that there's a point that it can be reached. And this point, known as the Chandrasekhar limit, is a point where one of these white dwarfs all of a sudden cannot exist anymore because the pressure trying to push and the gravity trying to pull all the atoms in together, that ends up exceeding the degeneracy pressure. So you figure all the protons and all the electrons repelling against each other, the force of gravity ends up becoming so great it actually makes the electrons and protons end up attracting each other. They get close enough where they can end up attracting each other, and that creates a new type of matter called neutron degeneracy, and that's when you get a neutron star. Now, you wonder, well, is there any case of this happening in the solar system? Yes, well, not the solar system, but the universe. Yes, there is. So there's systems like this that happen all the time, and take a look at this. Here's the same white dwarf, and I've put it around a red giant star, and you can see it's close enough that it's literally pulling mass off of this star. It's pulling mass off of it, and it's actually sucking it all up. So when this happens, what happens here is that this white dwarf is eventually going to suck up enough mass. You can't see the mass going up here, but the white dwarf will eventually end up sucking enough mass where what'll happen is that it'll end up going supernova, and it's in fact a very famous type of supernova, the Type 1a supernova. And the Type 1a supernovas are well known because we know they're all going to be the exact same luminosity. It's the exact same type of explosion, a white dwarf getting too massive. So we can use it as a standard candle in the universe. So we can actually figure out the distance to a Type 1a supernova rather easily because we know how bright a Type 1a supernova is going to be, because it's the same thing all throughout. And when a Type 1a supernova happens, we end up getting a neutron star. And there are two types of neutron stars. There's the magnetar and there's the pulsar. So here is a neutron degenerate star. Now, these things are absolutely insane. These are the smallest objects that we know of in the universe that end up not being black holes. This is pretty much as crazy as it ends up getting. So once the electron degeneracy pressure ends up getting exceeded, there ends up being one more pressure that can hold gravity back. One more quantum mechanical pressure, and it's neutron degeneracy. So once the electrons and protons end up merging together and creating a ton of neutrons, it ends up collapsing down to this size. And this size is not very big. You can see it's got about 1.4 times the mass of the sun. Really should be 1.44, but this is Universe Sandbox. It's not going to be 100% accurate. 1.44 times the mass of the sun with a radius of just 11.5 kilometers. That's not very big. So we're talking approximately 1.5 times the mass of the sun, which is huge. We are talking unbelievably massive. 1.5 times the mass of the sun. And all of that compacted into the size of Manhattan, pretty much. Or the size of New York City. That is utterly insane to me to think of. That these stars, they're so compact, they're so tight. And one of these things is so close to becoming a black hole that it's actually nuts that they're not black holes. If you take a look at the surface gravity on one of these things, it's just utterly insane. You can see we're talking almost 100 billion times the gravity that you would find on the surface of the Earth. 100 billion times. But again, that's only if you get into the surface. If you scroll out, of course, this is 1.4 times the mass of the sun. So the solar system's going to get a little messed up, to say the least. And you can see already, I played a little bit of this simulation, and it's already gotten messed up. So you scroll out here, but you see, despite having this 100 billion times gravity, on a large scale, it doesn't really matter. Because at these distances, the only thing that matters is the 1.4 times the mass of the sun. It only matters when you get in really, really, really close. And this is when gravity starts becoming very, very, very weird. Because this is when space starts getting warped to such a degree that we actually need to start taking in general relativistic effects. Because these pulsars are usually spinning at massive rates, we've seen pulsars that end up spinning at 24% the speed of light, which is, I think that is just crazy. Like, we have millisecond pulsars, and that's what we call them. They're spinning several hundred times a second, which is nuts that they're spinning several hundred times a second, and they're spinning so fast and they have gravity so strong that the spin of one of these pulsars is actually dragging space-time along with it. Although it doesn't end up getting as extreme to the point of a black hole, which is something that I will get into once we get over to black holes. This is a phenomenon that we're going to end up calling the ergosphere, which in a black hole, space ends up getting dragged so far along that it's actually impossible to stand still. Space itself is actually traveling faster than the speed of light, which is something that I know a lot of people think, how can space travel faster than the speed of light if nothing can exceed the speed of light? Space is its entirely own different thing. So although pulsars don't have an ergosphere, unless they end up getting way higher spin rates than milliseconds, which we haven't discovered yet, they do significantly pull space and time along with it. So although you would be able to stand still near one of these pulsars, it would be very, very difficult to do because you would need to travel in the opposite direction at a very high rate of velocity just to stand still near one of these things, because that is how much space-time is actually getting dragged along the rotational axis of these things. Now, if you're near one of the poles, you're fine because there's really no rotation going on there. But if you are along the equator here with the rotation, that's where the time frame dragging is going to be the strongest around one of these things, which is just nuts. And of course, you got to be wondering, well, there's got to be some point when one of these neutron stars end up becoming a black hole. And yes, there is one of these points. However, this is not necessarily really known, because like I said, we know a lot about electron degeneracy. We have an entire equation of state to talk about non-relativistic and relativistic electron degenerate matter. However, we do not have any equations describing neutron degenerate matter. It is such an extreme type of matter that we've never even been able to recreate it in a laboratory setting to even study it, to even get an equation of state for one of these things. That's how extreme one of these neutron stars end up being. So we don't even know. But our best guess is that if one of these neutron stars ends up exceeding anywhere between 2 to 3 times the mass of the sun, somewhere around there, 2 to 3 times the mass of the sun, that would end up creating what is a direct collapse. That wouldn't end up creating a supernova. It would end up just directly collapsing into a black hole. So that's what's going to end up happening here with a pulsar if it ends up getting too close. Well, how about neutron star collisions? Oh, yes. Neutron stars orbiting each other. Let's go ahead and take a look at what's going on here. Here we have two neutron stars orbiting each other, and they're orbiting each other very, very closely. It's a very, very close thing, and time is slowed down to such extreme extent here that it's almost hard to fathom. You think that, normally with gravity, you have orbits on the order of days, months, years. Well, these neutron stars, like I said, they're about 11. These are about 11 kilometers in radius. So you figure the distance between these two, and I can actually pull this up here. Let's see. Their distance between the two is only 150 kilometers. with gravity such as strong as this, because they are so close together, the gravity is unbelievably strong. But you would think then, oh well, then you would have tidal forces. You would be right with the tidal forces here, because the tidal forces would be absolutely extreme at this level, because the gravitational force on one side of the neutron star is going to be way stronger than the gravitational force on the other side of the neutron star. But, 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 the unbelievable strength of the crust of the neutron star prevents those tides from even affecting it. So the tides are not going to affect these neutron stars at all until they are basically on the way to colliding. Now, this is, of course, this is just a computer program. There would be no way to actually simulate one of those neutron star impact things and have decaying orbits. And then you would end up, in this case, end up getting the supernova with a gamma ray burst and end up creating a black hole. So we're talking here time scale 1 millisecond per second. So this is going 1/1000th times real speed. I wouldn't actually be able to even send this simulation up to real speed. If I did, the game would yell at me. So I wouldn't even be able to get this up to real speed. But just as a size comparison, I'm going to stop this here and I'm going to turn this camera over. There's Mercury. It's getting pretty burned up right now due to immense tidal forces, but there's Mercury. Mercury at this distance is only 42,000 kilometers away, which is not very far. So 42,000 kilometers, that's way closer than the moon is to Earth. Way, way closer. And again, these two stars, 11 kilometers radius each, 150 kilometers out, and that's 40,000 kilometers away from those neutron stars. And again, that's just to give you a sense of scale of how small these things are and how incredible these types of stars are. It's just, it blows my mind every single time I end up getting to talk about these, because it's such a mind-numbing concept to come across with matter that ends up being this dense. It's just, it blows my mind to talk about one of these things. It's crazy. So obviously these two things, they end up colliding, supernova. There's nothing else stopping a total collapse. What ends up happening here is that the solar system, well, let's go ahead and put a black hole in the center of the solar system. Well, we have a black hole here, 3 times the mass of the sun, because again, that's about the smallest black hole that you could be. You could put a 1 solar mass black hole in this game. It doesn't prevent you from doing that. But it's unrealistic, and I want this to be about as realistic as possible. 3 solar masses, it's about as small as you can get. And you can see that black holes are even denser than the neutron stars. So the neutron star was 1.5 times the mass of the sun in 11 kilometers. Here we have twice that mass. Twice the mass so we get 2 neutron stars, and it's within 8.86 kilometers. So we're talking about twice the mass, 2/3 the radius. So this is even more crazy dense. So that's going to make an even more crazy surface gravity. And we're talking now 500 billion times the gravity of the Earth. 500 billion times the gravity of the Earth at the surface of this. And we go ahead and we play this simulation out here. And once again, you'll see here that the orbits themselves, yeah, they are all warped out. But it's not like the black hole is actually like sucking things up like a vacuum cleaner. That's not what happens here, because that's not what the black hole's like. Now, one of the things you'll notice, and I love how they are able to get this, is that if you end up zooming in really close on one of these black holes, you'll notice the phenomenon of gravitational lensing, which is just incredible. Anytime that light actually ends up passing through a gravitational field, such as a black hole, it ends up warping it. It ends up going around. And the thing about a black hole is that it actually bends most of the light around it. So you can pretty much see all of the light that is behind it ends up getting put out here to its event horizon because you can't see through it, obviously. But that's why the light's like that, because the light ends up literally getting bent around and it ends up getting lensed. Just to give you the idea of how powerful the gravity of a black hole is that this is actually noticeable. You can actually verify that this phenomenon happens experimentally with the sun if you really closely watch eclipses and watch where stars are in the night sky. Well, where a star is during an eclipse and where a star is during the night in the night sky, you'll notice that it'll be off from where it usually is, and that's actually due to this effect of gravitational lensing. I think that's just crazy. So once again, so take a look at this really large blob of light here. I don't know what that is. I'll go ahead and scan it on over here. And you'll notice that it'll end up disappearing and then it pops out the other side. And that's usually how it happens. You'll see that it ends up getting warped through that. It's just nuts. General relativity is amazing. So that's what's going on here with the black hole. Now, of course, I wouldn't be able to talk about black holes if we didn't talk about when things get too close to a black hole and it actually does destroy stuff. So let's go ahead and destroy Saturn. Come on, we gotta destroy something. Let's destroy Saturn. Let's take the trails off. Now let's keep them on. Why not? Let's destroy Saturn. Look at that. Look at all the rings. They just blew away. Anything that got too close to the black hole ended up either getting slingshotted or destroyed. Yep, Saturn is here. Got too close to the black hole, lost a lot of its mass. Of course, it's also ridiculously hot now. And now Titan's coming in for an approach. And it gets pretty close to the black hole, but not close enough. I'm trying to figure out what actually happened to the black hole here. Maybe the black hole disappeared. I don't know. But so you can see here that everything got sucked into the black hole, and just look at all the stuff that ended up getting shot out here. Oh, here's the black hole. It's way out here. So that'll explain it. So the black hole ended up getting shot out with the nature of Saturn's gravity. So Saturn got close, but not close enough to be completely destroyed. All of its rings just ended up getting spitted out with a gravitational slingshot, and you end up getting this entire mess. So the black hole didn't necessarily really consume things because, again, the object actually needs to pass within that few kilometer wide window. It's a very, very small thing that matter actually has to pass through to actually get into the black hole. Otherwise, it could just escape, no problem. So what actually happens is a majority of the matter that ends up coming close to the black hole ends up getting just gravitationally slingshotted away because it's not actually getting close enough to get sucked in. It can get very close, but not close enough, and it ends up getting flung off at a high velocity. So that's actually what ends up happening here, because the black holes are actually so small. It's very, very difficult to actually get a perfect collision where the black hole will actually end up consuming some matter. And again, so I want to show you here, maybe this will give a better idea of just how small one of these things are here. So here's the Earth. It's the Earth. It's a nice Earth. So you can see the Earth, a massive size. 6,371 kilometers. Black hole the size of the Sun, well, the mass of the Sun, would end up having a radius of about 3 kilometers. So zooming in on it, there it is fully zoomed in. And we're looking at the Earth through the lens of a black hole here. So you can just see just how much larger the Earth is than the black hole. But this black hole has the entire mass of the Sun within it. It's just completely nuts to think about that this is how small this black hole is. And of course, if I ended up hitting play here, this black hole completely destroys this Earth because, again, you know, we're only about a few hundred kilometers above the Earth's surface here, and we have the entire mass of the Sun only a few kilometers above the Earth's surface. Obviously, tidal force is going to rip the entire Earth apart. If I end up pressing play here, it would be just carnage. So that's just crazy. I'm not going to destroy the Earth. I'm not going to go ahead and destroy the Earth. I destroyed Saturn for fun, and I'll go ahead and do that because maybe there's life on Titan. I don't know. But as far as we know, there is no life on Saturn or any of the Saturnian moons. But yeah, that is a black hole centered above Colombia. I will say that's above Colombia. Is that above Colombia or Venezuela or Brazil? One of the countries there. We'll say it's above Colombia. So that gives a really good idea of just how small one of these black holes are. And it's just crazy. But again, like I said, it's not that it really does anything at super, super, super large distances. Everything's fine at super large distances. Like, I'll go ahead and go back here. Because the black hole doesn't do anything to this system. Well, kinda doesn't do anything. But you can see here that everything's kind of on an elliptical orbit now because of the way that it ends up working. But nothing's getting sucked into the black hole directly because the black hole's not like an infinite gravity thing, and an infinite gravity thing would be a lot worse than a black hole. That would just end up growing. That would be a black hole that would just end up growing, end up consuming the universe. And that would be something insane. And, well, Venus is gone. Guess it ended up getting too close there. Hello, Saturn. But yeah, you can see here that even though, obviously, with a black hole of 3 times the mass of the Sun, all the orbits getting extremely elliptical because of it, what you'll notice is that nothing's getting sucked into the black hole because nothing's going to ever get close enough to get sucked into the black hole because everything is at least the Sun's radius away at their closest point. Otherwise, it would have already gotten burned up by the Sun. So every single stable orbit in the solar system is already at least the Sun's radius away. So nothing's going to end up getting affected by just how small, the extreme gravity of the black hole. Because the extreme gravity of the black hole doesn't exist until you get within, get very close to or even within the Schwarzschild radius. And of course, the way that general relativity ends up working anyways is that if you end up, going through all the equations and stuff, what you'll realize is that space-time ends up hitting an asymptote at the event horizon. So that's why you actually end up seeing, whenever you end up seeing one of these diagrams describing a black hole, and they'll always show you like the cone-shaped hole, and a black hole is always shown as like an infinitely deep pocket of space, because there's actually, when you take a look at the general relativity equations, there's actually an asymptote at the Schwarzschild radius. So that's why we don't really know anything about the interior of a black hole. We would never be able to look into one anyways, because light wouldn't be able to escape it. No information would be able to escape it anyways. So we don't know if it's actually a singularity with all of the mass on it, or if it's like a small amount of mass in a very, very tight center, or if it's like quark degeneracy. That's something that's getting studied on right now to see if there are potentially quark degenerate stars, and that's what black holes are. It's really not well known. But I would say that even if there is a type of quark degeneracy, we've got black holes that are at the center of galaxies that are millions, billions, trillions times the mass of the sun. So even if we have, I would buy a quark degenerate star for, say, 3 times the mass of the sun or 5 times the mass of the sun. When we're talking millions, billions times the mass of the sun, billions times the mass of this black hole, there can't be anything stopping that. It's got to be some type of singularity, but we'll never really know because there's no way to experimentally find out what's inside one of these black holes. Of course, one of the things about these black holes is actually when you actually see someone falling into the black hole, things get really weird with black holes. Because if you see something falling into the black hole, because the way that space and time ends up getting warped, is that you'll end up seeing someone more slowly and more slowly end up approaching the black hole. And the reason why that is because time ends up going slower in a gravitational well. And this has actually been experimentally verified on Earth that there is actually a general relativistic warping of time, and there's also a warping of the energy of the light, the wavelength of the light, and it's actually called the gravitational redshift. As light ends up leaving a black hole's gravitational field, it ends up actually losing energy and its wavelength actually gets longer. It ends up getting reddened, as we would call it. Any photon trying to exit the black hole from inside the Schwarzschild radius, if it tried to exit, its wavelength would end up getting stretched out so long that its wavelength would actually become infinite. Any photon trying to leave a black hole ends up losing all of its energy. And that's really why. That's the way that anybody studying general relativity, that's the way that it is technically defined. That the Schwarzschild radius is the radius at which photons trying to leave end up getting infinitely redshifted. So anything trying to leave a gravitational well, it gets infinitely redshifted. And of course, there's different types of redshift. There's just your regular Doppler redshift, which let's say I don't know, Neptune over here was traveling at thousands of kilometers per second. We would be able to measure a pretty noticeable redshift on that. And that kind of redshift is actually how we're able to measure galactic rotation curves, which I think is actually a pretty good segue to go into galactic gravity. So, galactic gravity. How does this end up working? Well, this is a weird thing, and I'll fully end up admitting that. That galactic gravity ends up being a really weird thing. I don't know what happened here. But the galactic gravity, what happens here is that you'd think that there would only be the gravity at the center of the Milky Way, the center. So you have the gravity at the center from the supermassive black hole, several million times the mass of the sun. So we have gravity several million times the mass of the sun. So when you take a look at a rotation curve, so how fast things are orbiting the center of the galaxy, you would expect that the curve drops off to zero, infinitely far away, and then it slowly rises, and then when you get to the center, it peaks at the top. That is true for the center bulge of the Milky Way. That is not true for, say, any other part, which you'll see if you end up measuring a galactic rotation curve, which is what we do with radio telescopes, actually. It's something that we can do with radio telescopes. And these radio telescopes, what'll happen is we can go ahead and send a radio signal out to a nebula that's located somewhere within the inner spiral arms and somewhere within the outer spiral arms and somewhere else. And we keep on having discrete distances from the center, and we can measure how fast these nebulas are moving, and then we can get a good idea on what the average velocity is so much of something rotating around galaxy. Here's the strange thing that happens, though, is that you get what you would think is that, you get in the center bulge, and if you go in towards the center, velocity ends up actually going downwards if you get very close to the center. Of course, if you're in next to the black hole dominates, and so it spikes back up. But if you go in towards the center, the galactic rotation velocity actually ends up going downwards. And there's a peak of when velocity peaks. How fast something's going around the Milky Way ends up peaking. And that happens in the range of about one, what we would consider a megaparsec. Yeah, I mean kiloparsec. That would be a kiloparsec. 1 kiloparsec. And then it slowly drops back down, as you would expect it to. But then at about 2 kiloparsecs out, what ends up happening is that you get down to a speed of a roughly 230 kilometers per second. Roughly about 230 kilometers per second. And it ends up stalling out. And it stays 230 kilometers per second as you consider going further and further out. So 3 kiloparsecs, 230. 4 kiloparsecs, 230. 5 kiloparsecs, 230. 6 kiloparsecs, 230. You keep on going out. 10 kiloparsecs, 230. 15 kiloparsecs, 230. 20 parsecs, 230. And all of this is supposed to be dropping off like 1 over the square root of the radius. But it's not dropping off. It's staying the same all the way through, all the way out to the edge of the Milky Way, which eventually it does start dropping off. But that really gets astronomers thinking, because that baffles us, because we're thinking, well, what's going on here? Why would there end up being some kind of weird thing when the rotation would end up being the same exact speed throughout the entirety of the galaxy? Why would that be? That would make us believe that there's actually more mass in the galaxies than what we're seeing. And this is something that is really, really, really intriguing, actually. Because this means that there's more mass in the universe than what we're seeing. Way more mass than the universe than what we're seeing. So astronomers started thinking, once they figured this out, that's like, whoa, these galactic rotation curves, they're flat. They're not dropping off like they should be, as if the mass continues upward as we know. That's not the case. That's not happening. It's staying flat. So what's happening here? There has to be more mass in the outer halo of the galaxy than we know. And that's when the explanation of dark matter ended up coming on. And that's where dark matter ends up coming into play. So dark matter, this stuff is completely unexplained. It's something completely different. So we thought, okay, maybe this is all of the mass of rogue planets, asteroids, space junk, space dust, stuff that we can't detect. We calculated that out. Doesn't even come close to the mass required. Doesn't even come close. Does not even come close. Doesn't even put a noticeable fraction into it. So like, okay, so that's not even close. Oh, what about neutron stars and black holes? What about all the degenerate matter we could be seeing? So they went ahead and they calculated all the degenerate matter that they think that we cannot see. And they went ahead and no, that wasn't it either. So they were completely baffled at this point because we went through all the types of matter that we do know. That, okay, all of these types of matter, we do know this exists, but no, it can't be any of this because the mass is too small. Then another possible explanation popped up with the discovery of the neutrino. And you have the neutrino. And this is a very, 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 very tiny particle. It's a very tiny, electrically neutral particle, virtually undetectable. Billions of neutrinos are flowing through your body every second. You don't feel it. It's something that you'll never feel. It's something that you never notice because they don't interact with matter in any way, really. You can't see it. It's very hard to detect. I mean, you got to consider a neutrino detector. They're using vats that are absolutely gigantic to be able to just detect one neutrino collision. It's nuts. So neutrinos end up getting discovered and they end up getting. So they think that neutrinos, maybe they're the source of dark matter. So they thought of, okay, here's what the average neutrino density would be in the universe. So they went ahead and realized, okay, well, really, what the average neutrino density would be for the galaxy. So they ended up getting a good idea of what the neutrino density was for the galaxy. So they went ahead, but the neutrinos are so ridiculously massless that doesn't even come up to be a measurable fraction of the amount of mass that is required to explain galactic rotation curves. So everyone just at this point was just stumped. So it can't be asteroids, it can't be black holes, it can't be neutrinos. So what is this stuff? What is this? So there ends up being an explanation that we just end up calling dark matter. It doesn't interact with light in any way. It doesn't interact with any matter in any way other than strictly gravitationally. It can't interact electromagnetically, obviously, because we would be able to detect it in some way. Even though black holes technically only interact gravitationally, at least with black holes, we are actually able to detect accretion disks around black holes, and that's the electromagnetic interaction that they have with us. With dark matter, the only type of interaction that we see is strictly gravitationally. So we aren't able to detect this. There's no experimental lab proof of this whatsoever, other than these galactic rotation curves. And when we take a look at distant galaxies, we take a look at the same gravitational lensing that happens with black holes. Well, gravities have a ton of, gravity. Galaxies end up having a ton of gravity. So they end up warping light as well to a significant amount. So we take a look at galaxies far away, and we take a look at the way that the light ends up getting lensed around gravities that are distant, very distant. And we realize, there's not enough mass here either. It's getting lensed way, 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 way more. So that's even more evidence for this dark matter that supposedly exists. So even that is way more evidence for this dark matter. So there is another potential explanation, which is called modified Newtonian dynamics, that ends up trying to explain at least the galactic rotation curves, where if there is a very, very small amount of acceleration. Acceleration on the order of 1 nanometer per second squared. Completely, almost unmeasurable accelerations, which that's on the order of the acceleration that you would see in a galaxy, even though these stars are moving at several hundred kilometers per second. The galaxy is so huge that the actual centripetal acceleration of one of these stars is almost negligible. It's almost zero. It's on the order of 1 nanometer per second squared. And if you end up putting in a constant of, I think it's a tenth of a nanometer per second squared, and you end up modifying Newton's equations with that constant in it, you are actually able to predict, almost perfectly predict, the rotation curves of these galaxies, which is great that ends up predicting it. We don't need any more mass. Oh, hold on here. First off, it doesn't meet conservation laws of the universe, and that makes any type of physicist very, very, very upset. Whenever you break a conservation law, it does not follow the conservation of energy. Energy is not conserved here. Obviously, energy is not conserved. So it's acting like this small acceleration is actually creating more energy in the gravitational orbit. So whenever you break conservation of energy, alarm bells start going off. You can't do that. And modified Newtonian dynamics doesn't explain the gravitational lensing because that really only works with mass. There's no distance element there. There's just the mass element there, really. So that doesn't have anything to do with acceleration. So modified Newtonian dynamics does nothing to explain the gravitational lensing. So we still have the missing mass problem. And not only do we still have the missing mass problem there, but there's even more mass in the universe that we don't know of, and that's due to dark energy. And that gets into an entire sect of cosmology that we really don't need to go into here. But just basically a brief thing of what happens here with dark energy. And dark energy is not dark matter. It's two completely different things. What we notice is going ahead, taking a look at galaxies once again, and taking a look at the Doppler redshift, as I was talking about earlier, where we are now hitting all 3 redshifts in one video. This is amazing. So we had talked about the gravitational redshift of a black hole. We talk about the Doppler redshift with our ability to be able to detect the rotation curve of galaxies. Now we're going to talk about a cosmological redshift, because what's happening with the cosmological redshift is that space, as you know, is expanding all around us. It's expanding like the space itself is expanding in the universe. It's on a massive scale, in an intergalactic scale. So it's not on the scale of, say, the solar system, so we wouldn't be able to notice it there, but on the scale of intergalactic space, we're absolutely able to notice it. So with dark energy, what that is it's basically a type of reverse spring. It's a weird type of spring. The way that we model, of course, with springs, ends up happening is you have 2 points, of course. You pull them apart, and there's a force that wants to attract the 2 points. You pull them apart more, and there's a force that wants to attract the 2 points more. You pull them apart more, and the force gets stronger and stronger and stronger, and eventually gets to the point where you can't pull it anymore, and you let go of it, and it snaps back to its normal form. That's a pretty traditional spring. Dark energy is something extremely weird, because let's say you have the 2 points again. Say it's the same string. Say it's the same spring, rather. You have the 2 points, but instead of attracting each other, what happens is that the 2 points repel each other. So you take the 2 points, they repel each other, so they move out naturally. Now that they're further apart, they want to repel each other more. So they move. So they move even further apart. And they want to, and the force repelling them gets even more. So they move even further apart. And that starts accelerating the distance between the 2 points. And it ends up going crazy. So that is what is dark energy. It's causing this weird reverse spring in the universe where 2 points end up getting further and further apart, but the further apart they are, the more they want to repel each other. So that's how we're pretty much modeling the expansion of space. And the cosmological redshift is that as a photon of light ends up moving through space, if it's moving through a long, talking gigaparsecs of space at this point now, a long stretch of space, the photon would end up getting stretched out and end up getting lengthened and redshifted to the point. And it looks like that it would look like that the galaxies are moving away from us. So it looks very much like a Doppler redshift. It almost looks exactly like a Doppler redshift. But it's not a Doppler redshift. It's a cosmological redshift. It's actually how much space has actually stretched out that photon, and the photon, how much energy the photon has ended up losing over time due to the expansion of space. That's what ends up causing the cosmological redshift. And that's how we know that space is actually, the expansion of space is actually accelerating, because we can see as we look further, further out, that this redshift is getting more and more and more, and it was not getting as more and more as it was in the past. So we can see a quick spike up in the redshift and then starts slowing down a little bit. So that's how we know that the acceleration of space is actually getting faster with time, because the redshift is getting more quicker now that it's closer to us. So just as a recap, we've gone over all the types of degenerate matter. The electron degenerate matter, neutron degenerate matter. We've gotten black holes, neutron stars, and white dwarfs, and we've gone to galaxies and explained dark matter and dark energy. I think this was a really fun presentation, and I hope you guys enjoyed this too, as much as I love doing this. Unfortunately, there has only been an hour assigned to me for today, and I am going to have to go at this point in time. But thank you very much for tuning in to just listen to me talk about this stuff. I absolutely love astronomy, and I really hope that Nathan Force 13 are able to let me come on here more and talk about this stuff more often. Thank you guys for tuning in, and you all have a good day.
You're watching Force 13's live streaming service. It's June 30th, 2019, and this is the live Tropical Weather Bulletin at this time. Alvin, 94E, and 4W, also 94B, which isn't marked on this map for some reason. We're out to 29 storms around the world so far in 2019. Nothing going on in the Atlantic at this time. It's day 30 of hurricane season here, and nothing on the horizon anytime soon. The Eastern Pacific has the remnants of Alvin and 94E staying at 90% chance at the 5 p.m. PDT update from the National Hurricane Center. 4W is a tropical storm in the Western Pacific, not too far from the Philippines. It's been given the local name Igay, and it's likely to continue towards the northwest. No systems active in the Southern Hemisphere at this time. I think this is the point where we switch over to the other thing. Okay, excellent. I'm just trying to fix some things because things went a bit crazy there because that bottom bar isn't up to date, but I'll get onto that in just a moment. There we go. Alright, this is the current one. We were using our last one there. It's been so hectic. I hope you enjoyed what we just saw there, the Astronomy Hour from Devon. It was a fascinating show. But now let's get on to what's going on in the world of storms in this hour. And we've got a whole hour to talk about it. I'm joined by the team, which consists of Ryan, Hank, and Max. Good evening to you all.
Good evening.
Great. Just trying to wonder why there isn't anything working there as well. Okay, the Central Pacific page wasn't working properly. Okay, this is satellite imagery of 4W on the screen right now, and I suppose, guys, this might be the one that we want to start talking about because it is the strongest system that's out there right now.
Yeah, sure. Right now it's pretty disheveled, but it's getting better organized. It's having some issues actually gaining organization, and by that I mean stacking the low-level center with anything in the mid-levels, which right now it is not doing. And when that happens, then you can't have a vertically rising column of air, which a tropical cyclone would need to flourish and generate more symmetric and organized convection, which not 94W, I'm sorry, 4W now is trying to do. Still doesn't have a name from the JMA. Kind of surprised that it hasn't done so yet, but that probably would be coming on the horizon given further strengthening. It actually has weakened a little bit today. ATCF had it at 40 knots at the 12Z advisory, and then they brought it down to 40 miles an hour.
That's that's the second time they've done that today, actually.
When I don't know when that other time would have happened, but because it went to 40 knots at 12Z and then down to 35 knots right after the 18Z advisory. But this thing is not particularly well organized anyway you slice it, but it's probably getting there. It's going to be tough because some of the models have been kind of iffy on this system, particularly the global dynamical models have not been picking it up very well, trying to merge it with the monsoonal system over the South China Sea. The only models that are really picking it up right now are the H-Wharf and some of the other, I guess, regional models that have been trying to pick it up. But apart from that, and even then, it's not ridiculously strong. If anything, I think the H-Wharf has a minimal hurricane or typhoon, I guess, and that would be the maximum strength that it would get to on the models, if you go by dynamical models, that is. So. Yeah, right. It's not looking like this will be a significant typhoon or anything.
Just try and grab some of those. Well, first of all, actually, let's take a look at the JTWC track for Tropical Storm 4. I think this one is up to date. The 9 p.m. track eclipsed the southern tip of Taiwan, according to them. Maximum wind speeds of 65 miles an hour. We were surprised when they put out their first map, some of us, when they were going with 70 miles per hour because the models didn't really support that. What are they looking at? Because the GFS, at least, which is usually holds a lot of weight, isn't really buying it at all. And then there's the other issue of that potential feeding of another storm in the South China Sea that could occur.
Yeah, that's that monsoonal system I was referring to that's absorbing some of the energy, at least on the model from 4W. And it's possible that something like that may actually occur. And I think that's kind of the reasoning behind why this track is farther towards the south than it was initially. Initially, it was kind of further north to the north of Taiwan. Now it's kind of shifted farther to the south, and a little weaker as well. Yeah, neither the GFS or the European are developing this in any way, let alone bringing it in towards Taiwan as a strong tropical storm. The only model that really supports that solution as of right now is the HWR, or the HWRF, whatever you want to call it. And even that's starting to back off more because the most recent run is barely showing anything, in fact.
I think there was also the COTC that has borderline typhoon, if I'm not mistaken.
I don't pay attention to that model, so I wouldn't know for sure.
That's related to the Navy, though, isn't it? So JTWC might be thinking about that one.
Possible.
All right, there's also the Pegasus track map as well, which I think has it ever so slightly further north, but really not much difference. Depression all the way through, according to them. As you can see, they've named it. Igay is the latest name from the Philippines. And I don't think they're going to be issuing any warnings at all for the Philippines from this.
No, it looks like it's going to be passing to the north of Luzon.
So that's another view, and this is some of the computer models there. You can see some of the more familiar faces, CMC taking it further north. Do we ever believe that with anything, even when it comes to track forecast for an existing cyclone?
I mean, it's okay. It has an okay track record. It's just terrible with Genesis because it overdoes it all the time. But I think that the CMC is also kind of a little later and a little weaker on that monsoonal system in the South China Sea. So that's one of the reasons why it's a bit farther towards the north on this, because it's not feeling any southward pull from that. But apart from that, it's also very weak on that run. It's just 999 millibars at most, and that would be happening tonight, if anything. So it's going to be a little bit of a rough road for that.
Interesting. Here's another look at one of the other systems, Invest 94E. One or two raised eyebrows that maybe they didn't increase the percentages to near 100% and we kept it at 90. Am I getting that from any of you?
Well, here's the thing, though. I think that it's just, there's not enough certainty to know that it's, like, forming immediately, because they usually only go with 100% if it's, like, going to form at the next advisory, which it doesn't look like it. Well, it might do that. I think it has a really good chance, but I don't think they have enough evidence to support that it's, like, imminent, that it's currently forming, if that makes sense.
Yeah, let me pull up screen share and see if I can get this running right now.
I'm trying to get some imagery here myself. Let's go back to some imagery that we did acquire from earlier of 94E. I was hoping it would animate. Okay, maybe not. Well, there is a still image of 94E.
Only really a small burst of convection might be enough to grant it tropical depression status.
Well, it's on the verge of that, and I have imagery up on my screen share
I've got it now.
So I can. Okay. So this is basically the system right now. I'm using this drawing tool that I adore. So this is the system right now. You can see it's still pretty raw, and in fact, it's huge right now. I mean, the convective envelope is about the size of mainland Mexico, just for some
Compared
semblance
to
right now.
Alvin, it is huge.
Yeah, Alvin, by the way,
It
this
is a-
dead swirly right here. Moving off towards the northwest and
Dreadful.
is dead. Don't worry about it anymore. Okay. So 94E, this is the system right now. And you can see it's pretty big, and as a result, it's having some trouble kind of organizing any potential convection. I was looking at some of these frames earlier, and there's quite a bit of southerly flow right on the east side of this big convective tower right here, as well as a lot of northwesterly flow right over here on the northwest side. So as a result, what I think is happening is that there is a closed low that has developed in here, issues that it might not be tight enough to actually be warranting of a tropical depression, I guess, upgrade. So it's going to be, it's really close, but it's just not quite there. It's going to get there. Essentially, we can basically call it. It's going to get there at some point. But it's going to take just a little bit more time for that to happen. And you can see even here, there's a little bit of a convective tower forming over that, so that might help to just kind of wound up the circulation a little bit more, so it can come tight enough to become a depression. You can already see there's very well-defined outflow right here. Dual outflow channels, that's pretty well established right here. It's still kind of embedded within the intertropical convergence zone right here, but it's kind of shaped in a form like this right here. So it's not particularly no, what happened there? So it's not quite broken off from that just yet. Let me refresh this. I'm just like, okay. All right, now I'm getting the wheel of death. All right, that's brilliant.
Oh dear.
Let's see. This will work. Anyways, what's happening right now is that it's still embedded within the intertropical convergence zone. And why are you popping up, Adobe? Go away. I'm sorry. There's a little bit of technical difficulties on my end, but so it's still embedded within it. But right now, it's getting very close to breaking off from the rest of the intertropical convergence zone. There we go. So you could. So let me just kind of give a little visualization right here. So right here, this is where the kind of flow is generally located. Let me see if I can redraw that real quickly here. Let's see, there we go. See right there. So that would be the general flow of the intertropical convergence zone. You can notice here that the low would be right in here, and you can see all this flow in here. All this northwesterly flow right in here is going to be pushing in to this little kink right here, and as a result, this is also going to be mounting up a little more as winds increase on this side. So what's going to happen is this is going to continue being pushed back as the winds increase here. And once these two lines intersect here, once this crosses that means the wave axis is broken and that there is a closed low here, and it will become a bona fide tropical cyclone. And then we'll continue to move off towards the northwest under the influence of the subtropical ridge and basically leave the intertropical convergence zone entirely and become its own.
Yeah, definitely. What models have been saying for a while, some of them, is that it will be a long-lived storm, which is pretty rare at this early point of the season.
Yeah, I noticed that as well. Seems most likely that it would be because there's nothing steering it farther towards the north to move into the anomalously cool waters off the coast of Mexico. But there's nothing that's going to be steering it towards the north into the North Pacific that would just kill it off anyway. So it's looking like it's going to stay pretty far to the south because if you note on imagery, it's already really far south now. Usually storms during June are close to where Alvin was. It's usually right off the coast of Mexico. This is about halfway between that and the equator. So this is pretty far south for a storm this early into the year. So this is going to remain pretty far south throughout its whole life, and even long-range models bring it pretty close to the Hawaiian Islands. There's no like certainty on what the impacts will be to Hawaii. It may just be rough surf. That's the most likely solution. I wouldn't be overly concerned about it just yet because it is, one, a long ways out, and two, the potential impacts are very uncertain because models just have no real clue to do what to do with it right there. So, I mean, this right here, this is already 10 days out. I shouldn't even be showing you that. So it's going to be a long time before it would have some impact to Hawaii. And even some of the models don't even have it surviving that far. In fact, the GFS kills it before it gets to that longitude. So it's going to be interesting to see
That's
how
what
the
it's
system
doing
evolves,
now,
but it's pretty
but-
certain.
A day or two ago, the GFS had it getting to 175 west.
Oh, yeah, you're right. But what's pretty certain is that this will become a powerful hurricane of some sort. Probably the first major hurricane of the season. I wouldn't doubt it.
Could be.
Yeah.
And then the storm. There's another storm behind it, which is also marked on the 5-day outlook. I think it.
Yeah,
30%,
I
they
saw
might have
this
upped it.
earlier today.
30%.
Earlier today, Hank, GFS and ECMWF actually hinting at a couplet of storms here.
Yeah, I noticed that as well.
Is there anything on this convective-looking area that seems to be pretty much on the borderline between the East and Central Pacific?
Sorry, say that one more time.
I don't know. Is there anything on this convective-looking area that seems to be on the borderline between the East and Central Pacific?
Yes, I did see that there was a little bit of support for that developing on the longer range. I think that the models have since dropped, but the Euro does form some sort of a strong disturbance. That's not actually a depression, but at least a decent looking system for, I guess, early July. So the main issue with that is that there's very strong shear over that. There's a pretty strong trough that's over the Central Pacific right now. It's kind of on the edge of the screen right here. And then it's kind of cutting across all this convection right here, so nothing is really able to get well organized right here. Well, as the case with 94E, there's the upper level winds here are very light, so it's not really an issue. And then afterwards, yeah, that couple of the storms that Nathan hinted to, it's possible that we may see something like that, but that would be in the long range. And it wouldn't be, none of these storms would be really affect to land, but it does appear that the second storm would be at a bit higher of a latitude than 94E, which, if it were to gain a name, it would gain the name Barbara, which is pretty likely to happen at this stage, just based on all the support. But you can see at the end of the European there's a little bit of somewhat of a Fujiwara going on between those two storms, but it's kind of far apart, so it's really a Fujiwara. It's just kind of two mutual storms that aren't really close enough to actually do a binary interaction of.
All right, we're going to get some more imagery up shortly. If you like, what am I going to say next? I was in the Super Cyclone Challenge mode then for some reason. If you've got any comments or questions for us whilst we're on the air tonight, please send us a message on the chat section. We're watching it closely. Tag Force13, start your message with us, and it will draw attention. We're now looking at the Western Pacific.
Yeah, I was just taking a look at this one right here, and it appears that there's increasing model consensus that this monsoonal system that I was mentioning would interact with 4W, may become a tropical cyclone in its own right. See right there in the HWRF right here, that's just on the coast of Hainan right there. That's probably, it could be a minimal typhoon right there, and then moving farther into the Gulf of Tonkin, and then making landfall around the Vietnam-China border by Thursday. GFS, I think, has a similar solution, but weaker with that, because it's just a very broad system, so it's tough to say. But it does have some sort of a tropical cyclone making landfall closer towards Hong Kong and Macau, as opposed to Hainan. I think the European is closer. Yeah, Europeans is more aligned with the H4 solution into the Gulf of Tonkin, and then making landfall in extreme northern Vietnam by the time we get into the middle of next week. And doing absolutely nothing with 4W.
Well, here we are. Latest satellite imagery of 4W looks like this. You can see that, well, both of those systems, you could call them, the one in the South China Sea as well, either side of the Philippines, producing significant amounts of convection. 4W is a lot more organized, and it's interesting to see what exactly will play out as we watch this. But as day breaks, 4W blowing up quite a lot. It's got a bit of a weird structure, though.
Yeah, that's what I was mentioning at the beginning of the stream, where it was kind of in a very decoupled state. That because those two, the surface center and the mid-level center, aren't vertically stacked, there isn't enough energy to concentrate to the point where you would have just a singular area of convection that would be pulsating up and down, and then would have like be gaining symmetry and all that fun stuff. It's just not in that state right now, so it's having two kind of distinct areas of convection, one in the northern quadrant, one a larger one in the southern quadrant, and that's just kind of the result of that misalignment right there.
I'm also looking here at Invest 94E here. There it is. Anything that we can deduce in addition to what you've been saying already from this imagery? Is it a closed low?
It appears so. It just doesn't look like it's tight enough to warrant a tropical depression upgrade.
Interesting. Whilst we look at this imagery, we've got some early questions in here. Do you think that 4W may become a typhoon?
It's got a shot, I'd definitely say. Definitely has a shot, but I don't know.
The opposite, actually.
Yeah.
You'd say what, sorry?
Yeah,
I would
don't
say
think
quite the
so,
opposite.
The opposite.
I don't think that it's going to happen.
I would say that it's probably not going to get much stronger than it is now, in all honesty.
Yeah,
blowing up
I mean,
those
most of the
clouds.
models have backed off on it becoming a typhoon. Most of them just have it staying as a tropical storm, so I think it's just going to, stay as a tropical storm.
Has a hurricane ever messed? Has a hurricane ever messed with California? Is another question we've getting here. It's not going to be any of these.
Yeah, but it depends on what you mean by messed with California, though.
Max, were you saying something there?
And I was saying, like, in terms of any kind of direct impacts, really only in 1858 and 1939. Mess with California, I don't know, you might be able to say something like Linda of 97 having that one cone that apparently to California at one point.
All right. And whoever's managing Force 13 US tonight, I don't know who that is. I'm guessing it maybe Tim, says that the US team is keeping an eye on the severe weather over there tonight. So Force 13 US is our one of our regional channels. We also relaunched Force 13 UK and Ireland properly recently as well. So if anyone is in my neck of the woods, that might also interest you on separate YouTube accounts and whatnot. Let's see. Do you think a new invest will sprout from the disturbance in the East Pac? Which one?
I'm assuming he's referring to the area of investigation behind 94. And just I guess just based on model guidance, it's pretty likely that it
yeah,
would
it's pretty likely
soon. At least once the incipient disturbance forms. Yes, it still has the 30% chance development in 5 days, whereas 94E has a 90% chance. It's pretty much, it's higher than that in all honesty, but it's given a 90% chance on the tropical weather outlook given by the NHC.
Absolutely. Okay. So there is the situation from the National Hurricane Center. That's the 2-day outlook. So you can see just another perspective there on just how large Invest 94E is. And what we do see with large systems is they sometimes struggle to intensify. Do you think we'll be seeing that problem?
It's tough to say because a lot of this convection is just there because it is still within the intertropical convergence zone. Once it does break off of that, then a lot of that convective mass will dissipate. So it's going to maybe struggle for the first few couple days of its life. But then after, I'd say Monday, Tuesday, probably Tuesday, that's when it will probably start to strengthen with a lot more earnest. Model guidance is kind of agreeing with that. The HWRF in particular. it wasn't very excited about immediate development. In fact, in the model run itself, I believe it only gets it up to a minimal hurricane by the end of the run. I take that back. The most recent run actually takes it up to Cat 2 and then levels it off after Wednesday. So and it doesn't start really intensifying it until Monday, Tuesday, because it's still kind of broad and just kind of has a little time to take to actually converge more of that energy and start to develop more of a bona fide core. It appears is what the model is suggesting on this. Even has a few smaller circulation centers apart from the dominant one that are forming at the beginning. So it may take a little while for this to really get going, but once we get towards, I'd say, the middle of next week, it'll probably start getting a lot of steam.
Something that we might also want to just bring up here, because something you posted remind me of that, Hank. A contentious issue that happened in the last few days regarding Sepat. Anyone's thoughts on that right now?
Regarding its tropicality?
We obviously, I think people know that we didn't give it tropical storm status because the only reason why it had the wind speeds, I think it probably had the tropicality, or at least subtropicality. It didn't have a circulation.
At the surface?
From what we saw. What do you think?
What do you mean we?
Well, from what ASCAT was putting out, never saw a center of circulation.
Huh.
Yeah, it really did look very disorganized, and I'm not sure if I would even call it a cyclone of any sort. It didn't have like a.
That's what makes a tropical cyclone, and in the
that's what makes it
in the
exactly.
scientific definition, not necessarily saying that it's a wrong thing to name the storm, but under the current conventions, it is.
Yeah, and it was really a
Jaguar situation.
Say again?
No,
Okay, that
Jaguar
was
was a front.
Jaguar
was a front. It was not a cyclone whatsoever. At least Sepat had cyclonic characteristics. Jaguar did not.
And was, I think, basically just a with a little swirly about it or something.
All right, we're looking at satellite imagery again from, is Go 17?
Oh, are you asking me?
Looks like it.
And if you are, then yes, it is. Just kind of getting a different perspective on it, I guess.
And you can just about see Alvin there as well. God, that one really capitulated very quickly.
Yep, considering it was a hurricane 48 hours ago, I think it was. Now it's kind of, sort of, gone.
So there's some
It's
rapid
just like
dissipation.
Yeah.
I wonder if anyone wants to give a mention to Invest 94B as well in the Indian Ocean.
Yeah, that thing.
It does exist.
Sure. We just
that's a
talked
thing.
about it.
That's a thing.
That's a thing. That's a thing, yes.
Okay.
Here
I don't know
it is
anything about it.
on the screen right now. Even neglected to put it in the opening titles today. Well, there is Invest 94B blowing up some convection just off the coast of India, not far from the border with Bangladesh. What's there to say about it? One of these systems.
It's one of those systems.
Okay.
One of those
Let's,
monsoonal garbage systems.
Okay. Yeah. Definitely looks like garbage. What is that? Is that just... That's not... Excuse me.
So we've not looked at
Okay.
anything to do with this, I take it. We don't know whether...
Yep.
I don't know. I'd say maybe the best we could get out of this might be, in most extreme case, land depression.
Land depression.
Land
That's
one of their.
That's actually a terminology
I
that the
know.
IMD uses sometimes.
Yeah, land depression when a tropical depression forms on land. That's basically what it is.
Could we have a quick look at those models and see if it develops anything out of this? Last I saw, it doesn't.
Let's see here. Let's have a look here
Hank's
and
just
see if I
going
can find
furiously
something.
trying to find the Indian Ocean basin.
Uh,
Well, there it
and it's just a very broad
Huge.
disturbance.
is. Makes me wonder why they.
Alright.
Oh well, and again.
Though
Maybe-
the Euro does have a little bit
That
more
is interesting.
concentrated energy as it makes landfall. I don't know where that is in India. I don't know my Indian geography. It looks like it's close to Calcutta.
Yeah, not too
So-
far away at all.
Yeah, so looks like that it was not an actual. It may be depression on that run, but it's not like anything that's out of the ordinary for this region during this time of year. So I wouldn't. I mean, it's going to be a huge rainmaker. That's going to be obviously the biggest concern, as is with any of these monsoonal type systems. But development seems, I guess, just based off the fact that I learned about it 2 minutes ago, unlikely.
All right, 1:30. Let's do a recap on what's going on around the world right now on this live tropical weather bulletin. So this, first of all, is a look at the different areas of the world. The North Atlantic on the top left-hand panel there. Not displaying too much at this time. Little area flaring up off the Yucatan Peninsula, but models are pretty damn sure, even the CMC, that nothing will develop in at least the next 10 days. The Indian Ocean on the bottom left there, looking pretty quiet. Some interesting little flare-ups in the southwest Indian Ocean. And also you've got, of course, 94B and is 94, I think. And in the Western Pacific there, quite obviously 4W. There is a close-up image of Tropical Storm 4W. Visible imagery now over the system. And you can quite clearly see that decoupling there. And it's getting more pronounced by the hour, Hank.
Yeah, I'm starting just looking at this thing. It's not looking like it's going to be able to organize much at all. There's also quite a bit of monsoonal shear in the areas, really hindering this thing from developing. In fact, that's what's really causing this with height is all this northeasterly flow over this region, just funneling into that developing monsoonal system over the South China Sea. So anything that really tries to get going here is going to have a really tough time strengthening.
Yep, this is Invest 94B again, so we'll move on from that. 94E, we had better imagery elsewhere. We'll come back to that in a little while. There's another alternative picture of 4W, and you can see the cloud tops, for its credit. It's managing minus 80 in both couplings, as it were. The southerly burst is way below minus 80 Celsius. And this is the Joint Typhoon Warning Center track map for 4W. They're pretty keen on it becoming a significant tropical storm not too far from typhoon status, 65 miles per hour as it clips the southern tip of Taiwan and then moves on into China near the same intensity. So that could still pack a punch if that was to transpire, but at the moment, not looking too much like that's going to happen. The Pegasa track map looks very much the same. As far as I know, they still haven't put out any warnings to speak of just yet. Again, looking at those models there, spreading anywhere from Hong Kong, which has a 14% chance of tropical storm conditions at the moment, to Japan. I doubt the latter. The former is somewhat unlikely. China is much more likely via Taiwan, or at least clipping Taiwan. And then there's also Invest 94E, and the models get much more spaced out towards the end there, but in general, they are all headed towards Hawaii.
At varying intensities, yes.
At varying intensities. Just a reminder of the Atlantic, nothing expected. The East Pac, 90% on Invest 94E now. That's been the case for a little while. The Central Pacific one is not loading for me at the moment for some reason, and there's a look at the Joint Typhoon Warning Center area, just 4W. That is pretty much the top and bottom of it. If you've got any comments or questions for us right now, you can send a message to us via the chat feature on the live stream. Alright, where do we go next? Let's go back to some of the imagery of 94E, which we're watching very closely for potentially becoming our next tropical cyclone. There it is, and that's how it has been looking throughout today. Is the convection becoming deeper in the latest frame?
Deeper, I can check on that real quick. I just have the visible imagery loaded up and check IR. Let's see. Like, if you look at IR, then it definitely looks like a lot more compact than as if you were to look at visible imagery, because visible imagery also counts not just the higher convective tops, it takes into account everything, so it looks like there's a lot more mass to it on visible than if you were to look at infrared. But infrared, you could see it's still pretty compact, but it's still pretty bright, and that's going to be the issue.
It's got eyes right now.
What's going on?
It's got eyes right now.
Not the type of eye you'd expect, though.
Yeah, I know what you're talking about. I can see what you're talking about. It's just the two convective towers around, or I guess the left one is where the closed circulation. Actually, it's one of the two. Is where the closed circulation is likely located right now. And looking at infrared, it's tough to really decipher, but I believe.
Right.
Let me just.
Some people are really bringing down their expectations. We've got a question here. Is anything expected in the Atlantic this summer?
Yes. You just have to wait a bit. Wait for like a month or two and something will form.
I've seen some comments going along the tone of, there's nothing going to happen in the Atlantic this year. Already, we're only at the end of June.
I mean, I would wait till the second half of July when this whole MJO pulse that's basically centered over the Westpac. In fact, you can just pull this graphic up really quickly here. This is from This is the MJO forecast right now. This is right now, and you can see that all the rising motion is based over the Eastern Pacific. Hence, why there's been so much activity recently. That, and coupled with convectively coupled Kelvin wave, it's meteorology terminology that y'all don't care about, so I won't talk about it.
I just want to remind everyone that the long-term average for the first named storm happening in the Atlantic is July the 9th. We've already had it.
Yeah.
Well, not really.
Okay.
Andrea doesn't count.
And the second one is August the 1st, so we got a long time to wait.
Yeah,
That's
I thought
on
that
average.
I think that like the second named storm on average forms in like late July, so it might actually be an early second storm based on average. On the averages, that is.
Okay.
Yeah. So
Alright,
this
Hank,
is
go.
the. Sorry, that was my fault.
No, I really wanted to bring home that climatological point there, but you go ahead now.
No, I'm talking about interrupting you.
No.
So yeah, this is the MJO pulse right now. You can see that there's a lot of upward motion over the Eastern Pacific right now, which is why there's a lot of that's the base reason why there's a lot of cyclone activity right now. There's more to it, but they're techie and annoying. So, and then you can see it slowly progresses towards the east. Now you see it does weaken in velocity, but that's also because forecast certainty goes down. So it's a lot tougher to actually decipher if it's going to be as strong as it enters the Atlantic. It'll start entering the Atlantic, as in the main area of the Atlantic, within the second half of July. And that's likely when we'll start seeing storm activity really ramp up again. Because the Atlantic right now is in a transitional phase. It's very much scarily akin, actually, to a year that some of y'all may know because of how infamous it is, 2004. A year that had no activity in June, no activity in July. August and September was off to the races, and and it was pretty bad year, to say the least. I think that
horrible
this year
for
may be
Florida.
quite similar to that in many regards. That and I mean, just the configurations for both the Enzo and the Atlantic itself are strikingly similar. But I digress. Basically,
so just to confirm,
what
Hank,
I'm-
it's the blue areas on this screen that are favorable, right?
Yes, the blue areas are favorable. The yellow, orange, red, that's where air is sinking and where it is unfavorable.
In which
I
case,
guess. That's
why aren't we seeing things popping up in the Western Atlantic already? You know, the Gulf, the westernmost Caribbean, because they're already in the blue zone there.
It does. It takes usually some time for all this to kind of settle in. Usually, the phasing is convectively active on the backside of this. This is just where the
Okay.
vertical ascent is mostly concentrated. And if you look at the Gulf of Mexico, there's quite a bit of convective activity going on, at least within the barriers of the Gulf. I mean, there's quite a bit going on over here in Texas right now, and that, in some sense, associated with the MJO being in a increasingly optimal phase. But in addition, as all this progresses towards the west, then that's going to become where it's kind of centered just to the east of the main area where we're expecting this East Pacific outbreak to happen. That's when it's going to be likely when we're going to have the most named storms, when it's just based off towards the east, because that's when it's most convectively favored. But then you can see this area behind it in the Central Pacific progresses towards the east. All this stuff progresses eastwards, by the way. And then it will move into this area, so we may have a down phase again of Eastern Pacific, but then come August, it may go up again. And in the Atlantic's case, it may go way up. So this is something that it's kind of a wait and see type of thing. But right now, I'm really getting scary vibes for the Atlantic right now. And
Damn.
it's not saying that it's for certain. It's just how I'm observing this. If I can get my words across correctly, that's just what I'm observing. But as of now, it appears that it's just going to be the Eastern Pacific show for the first half of July, and then maybe the Atlantic towards the second half. And by the show, I don't mean we're going to have an outbreak of storms or anything like that. We're not going to see long track kick bird hurricanes like any of that. We're not going to see. It's just maybe just an uptick in activity, maybe some homegrown storms in the Gulf or Caribbean or the Western Gulf, maybe an MDR storm possible.
Yeah.
Just kind of your standard July stuff. Nothing like, you know, we're not going to see Irmas and Florences pop up all of a sudden. So during July, I wouldn't bank on that.
Well, that's the first thing some people will be thinking about. Okay, let's take some more questions here. 94E is still elongated, but getting organized, says Justin. Can everyone here say what they think 94E will peak as?
I'd say currently, I'm gonna go with maybe a high-end Cat 2. I'm thinking, but I think major hurricane status is actually a decent possibility.
Yeah. I'm
Let's go
going with at least Cat 3, maybe Cat 4, possibly. Depends on how quickly this thing can get its act together and how long it progresses into the Western, or not the Western Pacific. Oh Lord, don't maybe say that. The Central Pacific.
It could get to the west.
It's not gonna go all the way to the west.
It could do.
It could. No.
I want a Hector. No more, please.
Do you think that 94E has a chance of becoming a hurricane in the next 5 days? I reckon so.
Yes.
Very likely.
Was Sepat a typhoon? We're getting these questions again.
No,
we did
it
mention
was
that.
not.
Another comment that came in earlier, the Euro was separating 94E into two systems, one towards Baja and one towards Hawaii. I don't remember seeing anything like that.
Yeah, I'm not. Yeah, that's not. I'm not saying that right now. Yeah, I don't know what that's. Yeah, that's not. At least that's not the case.
Why are... Hold on a minute. Oh, this is an interesting question, actually, which I'm not sure we'll be able to answer, but why are invests like 94B have near zero development chances, but in the East Pacific it can take up to 60% before they get called an invest?
I don't know.
Because everything
It's
that JTWC tags as a low chance is given an invest designation. for the Atlantic and the East, anything in the NHC AOR usually takes about a moderate chance for them to get some sort of invest designation. At least that's what I've observed.
Will
Not always the
2000
case.
will
Well,
2019
not always, but that's usually the case.
Yeah.
Will 2019 be like 2018 in the Eastern Pacific?
No.
I don't think
No.
so. No, 2018 was almost record activity in the East Pac. It's going to be
It was record high ace that year, so
record high ace, yeah, and almost I think was it like tied the record for the most amount of majors? Am I correct on that?
no, 2015 had 11, and 2018 had 10.
At 10. Oh, tied for the most amount of Cat 4s is what I'm thinking of. The most
I
amount
think
of
it had-
Cat 4s and a Cat 5s.
I think it had the most amount of Cat 4s.
It might
That
have.
would not surprise me.
2015 was close though. Yeah, but it was almost
tied with 1994 and 2 for Cat 5s, if I'm not mistaken.
yeah, there's that too. So 2018 was an extremely active year in the East Pac. I do not think that this year will be. I mean, we could see, an active season, but it's not going to be crazy active like last year was.
Looks like this Eastern Pacific season may end up more like 2017, because that year had a pretty big outbreak in July. Not as big as the year previous, but still a pretty significant train of storms that happened in July, and then kind of a downturn in August, and then August, September were kind of down phase while the Atlantic was doing its thing.
Well, of course, we don't know about that.
But also, I mean, I guess 2017 isn't too bad of an analog. Don't go home with that and say the exact same thing that happened. The exact same things that happened in 2017 are going to happen this year, because they won't. But it's another really decent analog that I've observed. That and 2004 are probably the two best ones we have. Not just based off the Atlantic side, but also the Pacific and even the Indian Ocean in some aspects, though that's not as influential.
Even like 2004, we do see the start of the Doki El Nino, if I'm not mistaken.
Yeah, it's kind of transitioning away from that. It's more of like just the warm pull is centered in the West Pac, and there's more of actually the Nino 3.4 region is actually below normal right now, slightly, but it is It went from El Nino state to cool bias neutral. So that's just the Nino 3.4, and then the area where the warmest anomalies are is based west of that in the Central Pacific. So that's kind of more akin to 2004, though not as aggressive. But the AMO stay as well in the Atlantic is similar to both years, 2004 and 2017. Not quite as vigorous as 2017, but and by that I mean how warm the main development region was in 2017. Not as warm as it was that year, mainly because there's a lot of cooling going on near and south of Africa because of all the West African monsoon oceanic heat energy input, but also because all the warmer water is slightly based a little bit to the north, but as the state of the NAO changes, the North Atlantic Oscillation, some of those warmer anomalies will likely continue to shift farther to the south. Basically, all of the anomalies will kind of shift southward. So the cooler anomalies will be more closer towards the subtropical Atlantic, not just South and Maritime Canada, but kind of shift farther towards the south, as well as kind of the horseshoe ring that's typical of your AMO pattern. That will shift south. So the warmest anomalies will more than likely be centered in the main development region, and that is what's concerning regarding hurricane activity coming up during August, September, and maybe October as well. Last year, this time, the main development region was cold, and we just had that random spur of Beryl and Chris in July because of the convectively coupled Kelvin wave passage, and that was it for the summer. And then once the MDR warmed up in late August and the MJO came into configuration, that's when the Atlantic started to light up more. And September was the month that year as opposed to August, which was one of the least active in history. Or at least in 2018, it was one of the least active in history for August.
All right, back to Tropical Storm 4W. If you've just joined us, the JTWC are expecting it to track towards the northwest. It's the headline tonight, and most agencies expect it to strike the southern tip of Taiwan before moving on to China as a significant tropical storm. We're casting a little bit of doubt over that at the minute based on its current appearance, but that's how they see it right now. And one or two models in agreement, but really not that many. A complex situation, you could say, because as we look back at the satellite imagery now, you can see that other little system to the west of it on the other side of the Philippines, which could be in competition. And some models, which models in particular was it, Hank, that predicted that system to really develop?
It was the Euro, the H-Wharf, and the GFS to a lesser extent.
Well, that's pretty good company between the three of them there. HWRF, our Model of the Year 2017, if we ever gave out awards. And the ECMWF is always up there as well, so interesting how both of those are calling for that. And there they are together right now.
Yeah, right now HWRF brings at least a minimal typhoon in the Hainan and then into the Gulf of Tonkin. The centering changes because this is supposed to be centered over 4W, and apparently this trough picks it up on this run, so it off centers it. We can see it on the bottom left corner here of the screen.
Are we able to
see it moves in the Gulf of Tonkin here?
Ugh.
Right on this run.
And how strong is it?
That appears to be a minimal typhoon. Let me put the winds on the
it's gotta be good.
right there. Wow, I was way overdoing it.
Oh,
that's a strong tropical storm on there, and then weaker even. It's just the low center is so deep because it's so big. All right. I just pressed the wrong button.
Interesting.
See the European. That's the United States. I don't want the United States right now.
A question just came in whilst you're doing that. Do you think 94E could become a PTC?
No, it's not impacting land, so no.
Yeah, that's the answer I was waiting for you to say, really. It just doesn't happen, really, in the Eastern Pacific. Has it happened yet?
I think the 2017, one of the storms was a PTC. I think it was a Lydia.
I think they did do it once. Just once.
I don't know. I wasn't paying too much attention to Lydia because Harvey was happening at the same time. That was knocking on my door, so I wasn't paying too much attention. But there might have been another storm that did it in 2017. I just don't know. Max, maybe. I'm not sure. Maybe one.
Don't look at me. I've not got a clue.
No, I'm not. Yeah, I don't know.
All right, looking back at this.
Okay, yeah. So this is the European model. You can see still pretty big right here over the northern and South China Sea, and then moves across Hainan into the Gulf of Tonkin, makes landfall in extreme northern Vietnam by Wednesday, so about 4 or 5 days out, and then moves inland and dissipates. The GFS, on the other hand, is weaker and more broad at the same time. A little bit of convective feedback erroring happened here, but it appears that the main low center would move closer towards Macau and Hong Kong earlier on, maybe closer towards Tuesday or Wednesday, or I guess it'd be Wednesday at that time in this part of the world. So it's Wednesday.
So as Sunday.
What appears to be a tropical storm. So, and then that would move basically along the shore until it gets further into Indochina, where it will eventually dissipate. Other models that no one cares about, say things, CMC, yeah, similar thing. It obviously develops it, but it at least has good agreement with the remainder of the models. So, and then NavGem, terrible model, don't care. So, you should hear me talk to myself when I do this sort of stuff. I just talk trash about these models, and it's kind of funny. I should probably record myself doing these sometimes.
Well, that'll be the blooper reel for 2019 sorted out then.
Oh no, it could make up the whole blooper reel if you wanted it to. But no one. But I hate the sound of my own voice, so I would hate that to happen. So yeah.
All right, we've looked through all of those, I guess. Let's see if we can get another view for the Philippine region here of those two systems. Just about to get there now. Yeah, here's another one. So you can see, if we speed this up here to an acceptable speed. Actually, in those latest frames there, it appears that the convection is waning in 4W.
Latest frames. Let's see. I see it on the stream. Yeah. Looks like it to me too.
Well, that can't be good.
No, it's not.
And
Nothing
on the
forming a
left-hand
top surface center
side,
either.
that other thing is maintaining generally, but it's got no shape to it, has it?
Nah, it's just a broad monsoonal system as of now.
As far as effects on land, parts of Samar might see a little bit of significant rainfall there. Catanduanes might get some inclement conditions very soon, later today, and the southeastern part of Luzon. But for the Philippines, doesn't look like there's going to be particularly big impacts at this point.
Yeah, I would generally agree with that, yeah.
Alright, Ryan, Max, any thoughts? Because we're just about to wind up here.
Not really.
Not really.
Ah, well that leaves us in a pickle for 5 minutes. Well, if you've got any comments or questions for us whilst we wait for the end of the show.
Ooh, let's read out some questions here.
Alright, there are some
let's
questions, yeah.
Go back.
In the
Let's read
Atlantic,
some questions.
do you think that there could be a storm like Sandy and make landfall in the northeast?
Who knows?
I
Who
mean,
knows?
who knows?
Do you think
That's good of an answer I'm going to give you.
Do you think the system on the west side of the tag does it?
On the west side of the Philippines? Well, not yet, but it might be down the road. I think it will be. Question there, is there a core forming in 4W? Not so
Nope.
sure about that.
Yeah. Oh, here's a classic question here. When will Barry form?
We've been waiting a long time. That is going to be the question of the year, I imagine. We're probably going to be waiting longer for Barry than we are for any other storm in the Atlantic this season.
Yeah, probably the biggest gap will be between... Yeah, I think this is going to be the biggest lull between storms in the Atlantic this season.
More than likely, I would say, yeah. Well, maybe, well, you could arguably say that we haven't seen any storms, but, well, tropical storms, I should say. So we haven't seen any tropical activity this year. Whatever Andrea was, and that's it.
Well, Andrea was a subtropical storm for like 18 hours and then it died.
I know, I'm just joking around about that.
Will there
So-
be a hyperactive comeback in Atlantic like 2010?
A hyperactive
2000.
comeback in the Atlantic like in 2010. Okay.
What? Okay.
Well, I certainly don't think the Atlantic quite as crazy this 2010. Uh-huh.
I don't know. I don't know what's going to happen with that. We're looking at latest imagery. Just to say, it's starting to get dark now over Invest 94E, so light fading. And I must say, Hank, I'm getting quite convinced that the eastern blob of convection is going to be the center of circulation here. Don't know what you think. Or anyone else, for that matter, as we look at it on the screen. Not sure whether it would make a huge amount of difference, but that's where we're at. It's way out at sea, won't be affecting any areas of land anytime soon, and that pretty much wraps up our tropical weather bulletin for tonight, guys.
Do you think the disturbance percent chance of impact this week?
Do we think the disturbance
Good
would oversect?
possibility. I think it's a good possibility.
And do we think 2019 worldwide could be similar to 2017? Well, a lot of things happened in 2017 worldwide.
Well, 2017, we gotta think. 2017 had a very active Atlantic, an average East Pack, a very quiet West Pack. So, probably not. I don't think.
Oh, well.
Probably more active than that in the worldwide sense, but I don't know.
That finishes up our Tropical Weather Bulletin live for tonight. Hope you enjoyed it. We were here. I mean, when it comes down to it, there isn't really too much to talk about because none of the systems are affecting land or are particularly strong in any way, and 4W looks terrible right now, but there we go. Tropical Weather Bulletin Light would have gone out at the start of today's show, but there's an error in it, so it'll be coming out in about 10 or 20 minutes on the Force 13 Twitter account. Until then, we'll have regular updates across social media, Force 13 on Facebook and Twitter, and of course our YouTube channel, which you're probably watching us on right now. Good night from us and from the team. Thanks for joining us, and we'll see you again soon. I imagine with a normal Tropical Weather Bulletin tomorrow night. We just went live really because we thought we would, and it came right off the back of the Astronomy Hour, which was really good as well. You can catch up with that, by the way. It's going to be archived on our Space channel. Did you know that existed, by the way? Our Space channel.
No.
Which I think you can find through our channel page, hopefully. Just have a look on there and look at all the associated channels, and if you like any of them, give them some support as well. We all need it. See you soon. Good night. Thank you.
Good night.
What?